Okay, our next presenter, let's get this up and running. Our next presenter will be Mark Walsh and Don Gans. No, I'm sorry. Yes, it is. Mark Walsh is the president and CEO of Gannon Technologies Group, and Don Gans is a statistician and professor at George Mason University, and they're going to present on the Flash ID system. This should be them. Come on up, guys.
All right. I'm going to try to turn the sound up again. It doesn't, just a little bit. All right, and not blow up the... Okay, just a little, yes.
Okay, so Don Gans will be first.
Thank you. 10 years ago, Mark Walsh, who's going to be joining me shortly, walked into my office and introduced me to a technology that was being used for handwriting character recognition. What's the content of the handwriting? With the proposition that that same technology could identify the writer of the handwriting. My colleague and long-term statistics professor at George Mason, John Miller, who's sitting in the back, said, "He's crazy, don't waste your time with it." But my whole professional life was a preparation for this moment. And Mark and I worked together, and within a few months, we had a computational solution that used that technology for handwriting identification. And out of that grew the Flash ID, the forensic language-independent analysis system for handwriting identification, and the document examiner workstation that the FBI is using. I'm going to tell you the key elements that make Flash ID work. The key elements: processing the image, then forming a modeling database of known writings from a database of writers of interest, and then using that analysis database in order to score questioned writing. And then we're going to tell you some of the testing results that have been used against our system, and Mark will tell you, give you pictures of functionality that's in the forensic document examiner workstation. Flash ID has a very well-defined frame for comparing writing. It consists of a method for segmenting handwriting, and then two important classifications of those segments of handwriting. Those segments are called graphs, and the graphs are, first of all, classified by something called isomorphism. It's a topological classification, and a meaningful classification by shape. That frame is what allows us to compare handwritings at the level of like with like, and I'll develop that for you. The image processing starts with a 30 dpi scan of the image, and then the creation of a 1 pixel wide skeleton of the handwriting. Then we finally segment that skeleton into graphs that we call protographemes. And the top line gives you one example of that segmentation. Protographemes, for instance, a Latin character might have multiple protographemes segmenting it. A protographeme, or let's say adjacent protographemes, are combined into something we call graphemes. So the protographemes grow graphemes. A protographeme can be a member or a part of multiple graphemes. There's redundancy in the system. We also sometimes, everything's automated. We have an automated simplification of some of the graphemes to embeddings. And in this particular slide, you see that the L in London, towards the bottom of the slide, is simplified. The O in London is simplified at the bottom of the slide. Again, totally automated procedures. I mentioned the isomorphism class. That's determined by the connectivity of the nodes and the edges that are in the graph. Again, a topological property. So no distortion of that graph that doesn't break it changes the isomorphism class. And an isomorphism class has a feature vector that's defined with it. For instance, the isomorphism class of this particular graph, which we call a T graph because you can deform that to a T, has a vector of about 200 physical measurements. Shape class is determined by geometric relationships of parts of that graph. And for instance, again, I'll point to this shape. The shape class of that, Joanne's telling me I could do it in an automated fashion.
So that people online can see.
She's always been a great mentor to me. And statisticians need that, particularly their professors. The shape that you see at the lower right-hand corner is basically the shape of an N. Flash ID has proprietary software that in a totally automated way do all the things I just showed you. Segment, define the isomorphism class and the shape class of all of the segments, form the graphemes, and again make those assignments. Flash ID is totally language independent. And the same algorithm that segments Latin writing segments Arabic writing, or any language is writing. We had noticed that mirrored English writing sort of resembles Arabic writing. We now move to the modeling that we do for a database of writers of interest, their known writings, putting them into an analysis database. The key element for that modeling is grapheme type. Grapheme type is a combination of the isomorphism and the shape, the two classifications. What that does, in particular, is allow us to compare writers that are very much alike. If we were to deal with a categorical summarization of a whole document, look at the frequency table of the grapheme types, then for a writer, if we take that frequency table of the writer's known writings, that characterizes the writer. And in some of our applications, we use that frequency table of grapheme types in order to do writership identification for a question document. Although when I talk about Flash ID, I'll talk about a different kind of modeling. That's modeling within the grapheme type level, again, where writers are most alike, and it's feature space modeling. We use those measurements, very high dimensional set of measurements, in order to tell apart writers whose known writings exhibit instances of that same grapheme type by pairwise comparisons of writers at that level. And then the information that we grasp from those pairwise comparisons is stored in a database for later analysis when we assess the writership of question writing relative to the database of interest that we used, that we modeled. Flash ID incorporates that grapheme type level modeling. In order to do it in Flash ID, we require an independent, a different reference set of writers, each one of which has a large corpus of writing. And then we have a database of interest of writers, the ones that we'll be searching later on in either closed or open set fashion. And we're going to compare the writings of the known writings of the people in that database of interest to the known writings in that unrelated reference set. And those pairwise comparisons at the grapheme type level are what's stored in a database for identification. Now the scoring. We start the scoring. We have a question writing, question document. We process it the same way we process the known writings. We skeletonize, we segment, we come up with a set of graphemes for that question document. And the way the scoring works, every grapheme from that question document, I'll call it an analysis grapheme, all writers whose known writings exhibited instances of that grapheme get a reward for that single grapheme. So if these two guys are in that class, I take that grapheme and I give each of them a reward. And I do that for every grapheme that we chunked out of that question writing. And what you're going to see is that the true writer is going to look more like those graphemes than any other writer through just random similarity. I'm going to show you that via a couple histograms that are on the next slide. And the way we formulate these histograms, we had a model database of writers of the London paragraphs, which you've seen a lot today. We took 5 available cursive paragraphs for these writers. We modeled them on 3, and we saved 2 for testing. And the histograms are going to show you, or for those histograms, we select one writer, and that writer's 2 held out London paragraphs become my question writing. And then we're going to score everybody in that reference data, or pardon me, in the database of interest relative to that question writing. I'll explain these histograms to you. If you look at the upper left-hand set of histograms, they come in pairs. The top histogram is histogram for all not actual writers in that database of interest, their scores for all of the graphemes in the question writing. And the second histogram is the same set of scores for the true writer. So what do you notice? The top histogram, which is random similarity, it's centered at 0, and it's pretty much balanced. Where the histogram for the true writer is biased to the right, to positive rewards. So this would be documents of one grapheme. Considering what we call graphemes as maybe a segment of a Latin character, it's not a very big document. But you can see that the true writer per grapheme is going to be more likely to get a positive score than any other writer through random similarity. If you look at the next pair of histograms to the right, what we've done is we've gone in and randomly sampled sets of 5 graphemes from that question writing, treated them like a 5-grapheme question writing, and then did the same kind of scoring. So what do you notice? On a 5-grapheme document, the true writer is a little bit more powerfully discriminated from random similarity. If we go to the lower left, we now have a 50-grapheme document, and we have a better discrimination of true writership. And now we move to a 125-grapheme document, again, what we call pseudo-documents by going in and doing the random sampling of that many graphemes. We have a very strong separation. And then the test, I'll show you again, relative to Latin characters and graphemes, the kind of identification that we can accomplish. We move to that testing now. We've reported in several, AAFS meetings. In particular, in 2009, we talked about both our closed and open set testing. This is based on what we call the FBI 500. 500 writers did up to 5 cursive paragraphs of the London letter. The slide here refers to 449 of them. 300 of them were taken to comprise a database of interest. And we modeled on 3 of the paragraphs. We're going to test on 2. The other 149 for the open set testing did not have, or not in the database of interest, and we're going to do the open and closed set testing. To do that, we're going to generate more pseudo documents. Again, this is a statistical exercise to see how accurate the system is. So I generate pseudo documents at various document sizes from 10 to 40 at a high rate of sampling, from 50 to 80 at a lower rate, and then for graphemes, because they don't correspond to Latin elements, again, multiple grapheme sizes. We're going to look at error rates. The closed set error rate, for us, wrong is if the document's not ranked number 1. For closed set testing, we need an inclusion criteria to decide, is the document in the database? Meaning, is the top-ranked document really a good candidate for writership? And our inclusion criteria is the difference in scores between the top-ranked and second-ranked candidates. The results, to show you the level of accuracy, this is for Latin characters. I point out again this result was just based on 11 lowercase letters of the alphabet with that very simple isomorphism, the T, what you saw the N here before. It comprises about 16% of the available information in a Longden paragraph. With 40 of those characters, you have very good identification. With 80, you nail it. And in the open set problem, you have 4%. I have to rush along. In the language-independent segmentation, you see the same level of accuracy. In 2010, we revisited the open set problem with a technology we call vector of count, and we were able to lower the error rate. And that's, as you can see, this test was given to us by USACIL. We just discovered it was David Parrott's set of 1,000 documents in the database, 56 documents with matches. We nailed 55 of them in first place. We got one in sixth place. We just learned that was the data set. It was given to us by USACIL. And here's an FBI test. I have to move so that Mark Walsh can talk to you about Flash ID. So you can read the results there. Again, open and closed set testing. Thanks, Mark.
Thanks, Don. Yeah, the data set has always troubled me because the one we missed was number 1,000, which was at the very end of the set. I've never had a chance to explore it, though. Again, very quickly, this is the application installed at the Bureau. It's similar to a lot of applications involved in forensics. Questions on one side, knowns on the other, and the workspace in the middle, and, of course, the customer's logo. I'll just talk about some of the features of the system. It's a fully functional system, totally lights out, totally automated. One of the features is side-by-side a comparison of the known and the question. This particular one's a bank robbery note on the left-hand side. On the right is the corresponding London letter for the writer of that note. Another important feature in the world of forensic document examination is building up for trial exhibits. The system has a heat map function which enables it to point out those particular graphemes or characters that had strong similarity to the known writings of a particular individual, and they will be shown as a color-coded heat map. Also, you can zero in, really drill down into the heat map in terms of building trial exhibits and pull out other pieces of information that you need. And all of this is very much exportable in real time for the document examiner. And then you can select text if you have a lot of material, a form or something, or multiple writers, some of which is of interest, some is not. There is a manual way to select text, or you can throw the whole thing in, and the system will match every writer on the particular document. Language independent, started out in English and Arabic, had recognition underneath it, as Don mentioned. Found out we could take the recognition out and deal with the atoms of writing, the loops, the cusps, the humps and the valleys, and retain the recognition power. So it's been tested on probably 20 different scripts. And then finally, where are we at right now? It's integrated within the Palantir analytical platform as a handwriting helper for analytical work. And we also have sort of a big data application. Again, this is more outside the world of forensic documents and more in a DoD-type application. If you have a bunch of stuff, you have thousands and thousands of pages, and you ingest them, and you have no forensic document examiner available, the idea is the system can take these in and it can cluster the documents. You can either find all documents that relate to a particular document, or you can build clusters among the documents. And that's it. Any questions, please?
We do have an online question, and I believe this one is for Don.
No.
The question was, what would the graph look like if the known writer is not part of the set?
We always get a writer who's ranked number one. And again, that's the open set problem. So what we do is right now, we look at the difference in scores between the top-ranked individual and the second-ranked individual. In my presentation, I didn't have time to go over it. I knew I wouldn't have time to go over that detail. But there are details about our vector of counts method. And we talked about that in AAFS 2010, which again is a categorical approach, somewhat different than the one I introduced before for, again, handwriting identification. So we do mix a couple of approaches to our technology in order to tease out more power. But anyway, the answer is we're always going to come out with somebody top ranked, and we look for indications that that's really very strong top ranked. Yes?
Always equated to a horse race with secretariat in the race, and when the sample size is small, it's very tight. And then as the sample size grows, the correct writer will tend to pull away, and that gives us that difference that we can measure.
Have you been able to derive some insights on an aggregate level in terms of, the graphemes that are most frequently observed, or, covariates in terms of, where the writers come from, demographics, and the kind of graphemes that you get to see, and so on and so forth?
I better pass that one to Mark.
Oh, you want to come to the podium?
I can use both. Stereo. We have done some work in that area, and we've actually found, again, very limited, almost anecdotal work, but we found national writing characteristics, for instance, certain features and writing from certain areas. And we've also found that the graphemes alone are to some level indicative of the writer. We use more information in Flash ID, but there is power if you were just to look at the distribution of the graphemes alone by the classification that Don mentioned. There is value there too.
My question is, do you require like items to be compared, like the same letters and letter combinations for this to work?
No, it doesn't care. It's what it does is it slices and dices the handwriting into graphemes. Graphemes may be characters, they may be parts of characters, or they may be groups of characters, or they may be something embedded in a character. And so it doesn't require the same text. It will just ultimately it will distill the graphemes, and as Don mentioned, what we're really doing is we're looking for the differences where things are most alike. So it finds the same grapheme of the same physical structure and shape, and then it does the statistical analysis on that.
Have you compared the writing of someone who's so their normal writing is in Arabic, so you have their writing, and then they write something in English? Have you ever done that comparison?
We have, and it's sort of the same thing between block print and pure cursive. There is not a lot of signal that we've detected. What is really interesting, one time we did find a person who had first language was Spanish, learned in Puerto Rico, then he moved to New Jersey and learned English through the Palmer method with nuns, and he actually had two completely distinctive writing styles, no overlap. Now, like if I were to write French right now, and I have tried it, it will match my English writing. But in his particular case, he built two templates in his brain for writing, with, I guess, pre-nun and post-nun writing. I went to Catholic school.
Why this thing works is two things. One, that writing really is persistent. And that's what my colleague John Miller didn't believe. When we converted him, he was the greatest convert in the world.
He said I was
being
crazy
a skeptic.
too, right?
He thought he was crazy. I usually say as a statistician, he was going to pay me, so I'd do it. But I don't always like to say that. It reinforces what you think of statisticians. But it's the persistence that there is power in a person's writing. And then it's the notion that this chunking up sucks that power out. And the true writer is going to be similar to himself more often than anybody else. That's the ultimate thing. So if you get enough information, you'll nail the guy.
Last question, Peter.
Well, this is sort of the inverse of enough information, and I guess you did this with the 1 grapheme, 5 grapheme, 50 grapheme. Have you tried to starve the system or to wean the system from information and see where it's a guess? We just don't have enough to go on. So from a rich sample or a lot of graphemes in common, but you've just got AOL on one side and whatever their competition is, but not some of the other remaining 20-something letters on the other side. So the graphemes really don't match. How low can you go?
Go very low. I mean, one of the tests that FBI gave us, sort of out of the box, was to have very short bank robbery notes written by people who had written this, participated in a database 3 years earlier. And they weren't given any real direction. So, I've got a gun, no die packs, give me your 20s and 50s. Combination of cursives and printing. And it was an open set problem. A couple dozen notes, 16 of which were in the had matches, 8 didn't. And we pretty much got it. So there's an awful lot of power in relatively few characters. We have 80 Latin characters will nail it. And then we showed you in particular 80 just of lowercase 11 Latin characters or Latin letters in that one most simple isomorphism. And that was because John and I could do that in our laptops real easy. And we prepared our 2009 AAFS presentation.
We'll have to hold that till the end. Okay. Thank you.